Satellite Y is orbiting Earth at a speed of 9.76 times 10 to the second meters per second. There is an electrical fault causing one of the fuel tanks to explode, increasing the speed of the satellite to 1.56 times 10 to the third meters per second. A. What is the radius of the satellite before and after the explosion? B. What is the radial acceleration of the satellite before and after the explosion? And C. What is the period T for one revolution before and after the explosion? To begin with part A, start with Newton's second law, which is the sum of the forces equals mass times acceleration. The sum of the forces is also equal to the gravitational constant g times the mass of the Earth times the mass of the satellite, all divided by the radius squared. The radial acceleration is equal to the velocity squared divided by the radius, so that way when you plug it in, you get the mass of the satellite times the velocity squared, all divided by the radius. When you rearrange the equation to solve for the radius, you should get the gravitational constant times the mass of the Earth, all divided by the velocity squared. Then for the radius before the explosion, you plug in 6.67 times 10 to the negative 11th Newton meters squared kilograms squared for the gravitational constant, and 5.97 times 10 to the 24th kilograms for the mass of the Earth. The velocity before the explosion occurred was 9.76 times 10 to the second meters per second. When you plug everything in, you should get 4.18 times 10 to the 8th meters. You do the exact same thing for the radius after the explosion, except for when you plug in the velocity of the satellite after the explosion, which is 1.56 times 10 to the third power. After plugging everything in, you should get 1.64 times 10 to the 8th meters. For part B, the equation for the radial acceleration before the explosion occurred is the velocity squared over radius. After plugging in the velocity, which was given, and the radius, which you just solved for in part A, you should get 2.28 times 10 to the negative third meters per second. For the radial acceleration after the explosion, you do the exact same thing, except you use the velocity of the satellite after the explosion and the radius after the explosion that you solved for in part A. Your answer should come out to be 1.48 times 10 to the negative 2 meters per second. For part C, the equation for the period of one revolution is 2 pi times the radius divided by the velocity. For the period before the explosion, you can plug in the velocity and the radius from before the explosion, and you should come out with 2.70 times 10 to the 6th second. For the period after the explosion, you plug in the velocity and the radius from after the explosion, and you should come out with 6.61 times 10 to the 5th second.